Hey kids, welcome to day 2 of our differential equations applications. So remember in the previous video, we talked about exponential growth and starting with the exponential differential equation, right? Which was the rate of change of y with respect to x is some constant times that dependent variable y. And that's what made it separable, was that your dependent variable was on the wrong side of the equation, right? But we said we could use calculus and solve this differential equation, but that you didn't have to as long as you remembered that yet was the solution. AP allows you to skip the calculus and go right to, I know how to get y by itself. If it is the differential equation k times y, I get y is equal to the initial y value times e to the kt, where k is the proportion, right? So again, that comes from the rate of growth. That's what the differential equation is. The rate of growth is proportional to the amount present. That's what ky says. So all I'm going to do here is use p instead of y, right? The rate of change of a population with respect to time being the independent variable and population being the dependent variable. So this is still, right? This is still the exponential growth rate. It is a differential equation and it is separable because the dependent variable is on the wrong side. So in that case, using p instead of y, then my solution solving that separable differential equation looks like PECT, right? The population is, how you can find population by just inputting time, is multiplying your original population times e to your constant of proportionality times however many years. So the question becomes, well, what if the growth isn't exactly exponential? Again, when you have a population, let's say you have a population of fish in your aquarium, right? So you have some fish in your aquarium. Can you just, and let's say the fish are reproducing at an exponential rate over time, well, what's going to happen, right? There's the aquarium has a, right? Your aquarium has a right, a fill. You can't, fill it if it'll get, I don't know why I can't talk right now, capacity, right? It'll get to capacity. So we're going to call the carrying capacity of our environment capital M. And things that affect the carrying capacity are how much food is available, how much living space, like the aquarium. What about getting rid of waste? What about disease affecting the population is growing, but then some people and some animals or some bacteria, whatever, is dying as well. So how can we model that with a straight up exponential might not describe it, right? Because an exponential equation, as you know, is a slide swoosh situation. So slide to the y-intercept, which is basically when, right, time starts, really. Time starts at a positive, and your zero, your y-intercept is your initial condition, and then you swoosh up forever, right? As t goes to infinity, that's not really realistic, that your population grows without bound. So there is another model. Instead of an exponential model, there's a logistic growth. And yes, logs is part of it, but of that word, but it's not a log equation. Because remember, a log equation also grows without bound. A straight up log equation, right, starts here, grows without bound, just grows a lot slower, right? Because it's just the inverse of the exponential. So the logistic growth model incorporates both of this swooshing off and growing quickly with growing, but growing more slowly. How the math works with that is that the growth rate, which is the differential equation, is proportional, so there's still a k, but it's proportional not just to the population, not just to y or to p, but to two things. Both the amount present, which is what exponential is, k times p, right? But also a fraction of that carrying capacity that remains after time. So look at this equation. How do I go from the exponential differential equation to the logistic differential equation? Both of them have k multiplied times the population. Both of them have that. But in addition, the logistic differential equation has a multiplier that is some way to describe what's happening to the carrying capacity, right? Is the carrying capacity being reduced by limits on food, disease, right? Limits on the actual boundaries of the environment. That's what this piece of the logistic differential equation looks like. So let's suppose that our carrying capacity is 100. If our carrying capacity is 100, I want you to think about what this expression inside the parentheses means. If I have 1, which represents a whole, right? Imagine multiplying kp times 1. If this was a 1, wouldn't the exponential differential equation and the logistic differential equation would be the same, right? However, what if it's not 1? If it's not 1, but it's 1 minus a fraction of the carrying capacity, a fraction of the carrying capacity, remember, assuming my carrying capacity is 100, imagine, though, that you have a very small population. A small population compared to your carrying capacity. So let's suppose you have only 1. 1 minus 1 over 100, isn't that still close to 1? So you would be multiplying over here kp not times 1, but something really close to 1. Which means the logistic differential equation is going to look very similar to the exponential one because you're multiplying it by something really close to 1. But it is smaller than 1, right? That's the minus. So there is going to be a slowing of the growth rate. As opposed to this situation, what if you had, instead of just 1, you had 99? Your carrying capacity is 100 and you have 99. Look at the expression in here now. 1 minus 99 over 100 isn't 0, but it's really, really close to 0. So what happens if you're multiplying kp times something really close to 0? It doesn't look close to kp anymore. It looks really, really close to 0. It's very small. Growth rate small. Growth rate small. Still positive. This number is still positive. Constant proportionality positive, population positive, multiplying by a fraction. So your growth rate is still positive, but smaller over time. That's where this logistic equation comes from. Logistic differential equation. So in here, the multiplier is 1 to represent the whole minus a fraction of the carrying capacity. How much population do you have compared to what is your carrying capacity? Now, I'm going to write this differential equation a couple different ways, right? And just notice that's just fraction work, right? I just got a common. I turned the 1 into m over m minus p over m. There's what that fraction looks like. Also notice that since this is over 1 and I'm multiplying two fractions, this is m times 1 is m, I can put that m wherever I want in the denominator. So this is what the logistics differential equation looks like. Or it could look like this if you want to put the m underneath here, doesn't matter. And just like the exponential differential equation, this logistic differential equation can be solved for P so that you have an equation that predicts population based on time, given that there is a logistic growth model. So I'm going to solve this logistic equation, and remember what you want to do. What you want to do is you want to avoid this math. So you don't have to take notes on this math because you don't want to do this. You want to be able to say, nah, just give me the solution. And remember, the solution to a differential equation is getting rid of the derivative. So the solution is P equals. That's what you want in your notes. Okay? You don't have to have all this math I'm about to go through. So if you want to just skip by it, fine. I will probably not be offended. But note that you will, right, if you're going on in math, then this is something that you're going to have to eventually do. So this is a separable differential equation because the dependent variable is on the wrong side. So I did some algebra and I separated it so that all my p's are on the left and all my t's and constants are on the right. Remember, k and m are just constants. So the left side is going to take partial fractions. So that's the math I did with the partial fractions work. Right, solve for a and b. Put it back into my differential equation, and then anti-differentiated both sides, and shocker, naturally out of this math comes ln, log base e. Using my rules of logs, I'm going to combine this. I'm also going to drop the absolute value because my carrying capacity is positive, my population is positive. I'm going to e to the both sides. Again, my job is to get P equals by itself. I reciprocated both sides. Note the use of exponent rules here. This is really 1 over e to the negative kt, positive plus c. So when you move, I move this back up into the numerator, which means I just negated the exponents. Got my 1, so I could add 1 to the other side, right? That's m over p minus p over p, which is where this minus 1 comes from. Add 1 to the other side. There's what p looks like. But I'm going to do a little manipulation of this e and the constant. Right, using the rules of exponents again, but e to the negative constant is itself just a constant. We're going to call this a this time instead of just another big C. And there is the equation that you want in your notes. This is the solution to the logistic differential equation. The solution to an exponential differential equation is yet. The solution to a logistic differential equation is a fraction where your carrying capacity is on top, m divided by 1 plus, what do we want to call that? Act maybe? I don't know. You figure it out. So there we go. Logistic differential equation, logistic model. P is by itself, got rid of the derivative. Now, I do want you to show, and especially if you look this up in our textbook uses a slightly different model. It kind of wraps up the m here But notice that since they eliminate the m in the denominator of the differential equation, it shows up in the denominator of the growth model, right? So I tend to, and I have seen and always used this one. They are the same, I promise. I promise. They are the same. You'll get the same math, same graphs, everything. So this is a handout that is linked on our page, and I'm going to go through this one example. Notice that they are giving me the logistic differential equation, the growth rate. This is the logistic differential equation. They have the m underneath k, and they want to find a formula for the bear population as a function of time. What that means is they want p equals. You don't have to do any math to get p by itself as long as you know the logistic growth model. Okay, there it is. Fill in your information. Get the information out of the words that your initial population was 10 bears at whenever we decided to start the clock, right? When the bears were introduced. So that's time equals 0. There were 10 bears, and I also have another piece of information that after 10 years, there were 23 bears. Please, please, please do not confuse this constant with p sub 0. They are not the same. That's what makes this different from exponential. A is not p sub 0. Do not just put 10 right there. So let's go ahead and try to solve for A. Solving for A. Use your information, use your initial condition. So I put the population is 10 bears at time equals 0. This is going to allow me to isolate A because after all, my original equation over here has a bunch, right? It has after I put 100 in it, I still have P, K, and T to solve for. But when I put in 0 for time, the K disappears. That allows me to solve for A. Now I'm going to go off into my workspace here for a second, and I'm going to show you how to, there is a formula if you want to always find A. For any logistic model, your initial condition is plugged in, and at time is equal to 0. Notice your e to the negative kt will always be e to the 0, which will be 1. Use algebra 1 and solve this equation. It's a literal equation, right? An objective from algebra 1, and solve for A. So this is the formula for any logistic equation to find A. M minus the initial condition divided by the initial condition. You can do that, or you can just do the algebra each time. It's not that bad, right? I cross multiplied 10 plus 10a is equal to 100. 10a is equal to 90. A is equal to 9, which is exactly what I would have gotten here, right? A is equal to 100 minus my initial population of bears divided by my initial population of bears. 100 minus 10 is 90. 90 minus 10 is 9. This is not your initial condition, but 9 is what I'm going to put up here. The interpretation of A is kind of cool, and if you look at this math, it kind of tells you what it means. It's not the initial condition. It's not how many bears you had present at time 0, but what it is that it says, given that your initial condition was 10 bears, A kind of tells you how many more groups of that size can fit into the carrying capacity. And that should make kind of sense, right? If I started with 10 bears, but my maximum capacity is 100, how many more groups of my initial population can fit in there? 9. right? So that's a kind of cool interpretation of what the interpretation of what A is. In exponentials, right, that value, that multiplier is just your initial condition. So now that I've found 9, I'm going to go and try to find K by I used my maximum carrying capacity, I used my initial condition. Now I'm going to use the point 1023, and I'm going to plug those values in, and I'm going to use my calculator to get K, and I'm going to not write down all of those numbers, but I'm going to store that value in my calculator. Notice that I wrote down a rounded value, negative 0.1, but in my calculator, I stored this value in my calculator. I stored it in alpha K because I just want it to be cute. And then when I put this equation, which I'm going to need to do, into my calculator, into Y1, I wrote 100, typed 1 plus 9e to the negative kt because I had stored K. AP expects you to maintain degrees of accuracy. If you have a calculator, they're expecting you to know how to do this. All right, so let's answer some questions now. As I said, I put this into Y1 and I adjusted my window, right? I made my Y max 100, and I made my X max 100. And you should be able to see this curve. It looks logistic. Notice that here's your initial population of 10 bears. And then you swoosh. But you swoosh, you're concave up while you're swooshing. Then there's a point of inflection, and you are concave down, and you don't grow without bound. You grow to the maximum carrying capacity. You are bounded. This graph is bounded at above. At M. So let's use our model and predict when the bear population will equal 50. You have a calculator. So please, please, please show the setup. You don't have to show any calculations. 50 is equal to, and 75 is equal to, and then give me your answer. Usually AP will say something like, for these, they always like you to round to 3 places past the decimal, but in problems like this, they usually say round to the whole year, just to avoid confusion. So what you're supposed to do with your calculator is you already have this equation in Y1. Please put 50 in Y sub 2 and find the point of intersection. When Y is equal to 50, X was equal to approximately 22 years. Then in Y2, I put 75. And I got approximately 33 years. Okay, now again, I showed because I have a calculator, when they asked me to use my model, I show that I used my model by plugging in 50 and 75 here, but then I let the calculator find the 22 and the 33 for me. Now look at this question. Evaluate the limit as t approaches infinity. You're like, what? Limits? What? Hello? Right? Doesn't that make sense? As time goes to infinity, this model is bounded above. So the limit is going to be the carrying capacity. Right? This whole thing is going to go to 0. So you're going to have 100 over 1, which is 100. This is a really, please in your notes, put a star beside this. This is a fairly common question on AP. If they have a logistic model in here, they like to ask this question because after all, they let you skip the calculus. Remember, this is the solution to a differential equation where the rate of change of the population with respect to time look like that, right? You didn't have to solve that using calculus. You were allowed to go right to the solution and then solve for your A and your K. So here's where they're going to get you with some calculus. When is the rate of the population increasing the fastest? What is that asking you? When is a time question. So your answer is going to be a time. When is the rate of the population? Rate of the population. That's the differential equation. So when is dp dt increasing the fastest? What do you need to do? You need to find the derivative of that. Well, this is the first derivative, so you need to find the second derivative, but hello, kids. When you are taking a derivative and the dependent variable is on the other side, what does that mean? What's the math that you need to do? Now think, you've been in integration mode. When you're doing an antiderivative and the dependent variable is on the wrong side of the equation, you need to do separable differential equations. When you are taking a derivative and the dependent variable is on the wrong side, you remember what that was? Yep. Implicit differentiation. So remember, K over M is just a constant. So here is my derivative with my constants plugged in. dp dt, right? This was my K, 0.1, it was really 0.09, blah, 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 blah. So I stored that value over 100 times P, right? This is my M, right? I can see where the rate of population is increasing the fastest, right? I can see it. This is my original. Point of inflection is where the highest slope is, right? Steepest slope. The point of inflection on the original is where the second derivative is equal to 0 and changes sign. Oh my gosh, second derivative test for concavity and poi. Changing from concave up to concave down on the original is where the first derivative has a maximum, right? So I could look at this and find where it has a maximum, but you're on a calculus test, so anytime you are asked for a maximum, right, it's also where the second derivative changes from positive to negative. So here I go, I just distributed 0.1 divided by 100, P times 100, the 100s cancel out, and I just get 0.1 P, minus 0.1 divided by 100 is 0.001 times P squared. This is a quadratic. The second derivative using implicit differentiation is, now I've kind of cleaned it up here, so I'm going to go through it. This is a constant time, so 0.1 times dp dt minus, bring down the 2, times 0.001, copy over the p to the first, that's a 1, not a prime. Spit out the derivative of the inside. All I did was factor out the dp dt. and I have 0.1 minus 2 times 0.001p, which is 0.002p. Now remember, the rate of change is positive, right? The slopes on this graph are all positive. Since dp dt is positive, I have, right, I'm looking for where does the second derivative equal 0? Well, one of the factors is always positive, so I just need to know when this factor is equal to 0. Do some math on that, subtract 0.1, divide by 0.002, and I get p is equal to 50. This is linear, right, with a negative slope. So with a negative slope, the second derivative changes from positive to negative, which means p changes from concave up to concave down, which is what I already knew. But I needed to know when. Remember, I was asked a time. Is my time 50? No, p is 50, right? This is the dependent variable, and they asked you when. When to the nearest year does the rate of population start to decrease, or when is it increasing the fastest? Those are the same questions, right? Same question. Plug 50 in for P. Wait, I feel like I already did that. Oh, snap, that's called planning, right? You already did this. So I did this at the beginning of the worksheet, but in reality, AP is probably going to ask you to do it here. So show you have a calculator, you don't need to do this math. Show that you have put 50 equal to your growth model. So again, your growth model is in Y1, in Y2 is 50. You're going to do your intersection, which is what we did before, round to the whole nearest year, and we get 22 years. Hey, wait a second. 50 was the population right when my population was growing the fastest and then started to decrease. On its way to what? On its way to the carrying capacity. Hey, what's the relationship between 50 and the carrying capacity? And the y coordinate of the poi? That will always be so. Always be so. Put this in your notes. All of this should be in your notes, right? But I know you're on a worksheet right now. Please, in your notes somewhere, this will save you time. I did the math and the calculus to show you. You don't have to do that if you know this formula, right? So there's a lot of parts about this applications where AP allows you to cheat with formulas. If they ask you where the rate of change is increasing the fastest or where the population growth starts to slow, which after all, isn't that what you want? Think about spread of disease. Don't you want to know when it should start to slow down? That is an actual application of logistic growth, right? And the calculus and derivatives and second derivatives. When is the point of inflection? It's kind of critical. The carrying capacity divided by 2 is always the y coordinate of P, and then you have your logistic growth model where you can solve for that time. Okay, so crazy. So for us and bears, what do we know? We know that we introduced 10 bears at time 0, right? Then at some point we had 23 bears. right? After 10 years, we had 23 bears. Based on that information, and we were able to, knowing that we had a logistic curve, make this prediction of how many bears given a carrying capacity of 100. And further, we know that after about 22 years, right, the population is going to grow pretty quickly. After 22 years, the growth is going to slow, right? And if you think about it, 22 years, right, ain't that long. So after 22 years, bear population is still going to grow, just not as quickly. Pretty cool, right? All right. I will see you in our next live session.